So welcome everybody to the first session of the third day of the conference. This session will be conducted by Shraddha Mishra from IIT BHU. And over to you, Shraddha.
Okay, thank you, Arna. And I will first invite our first speaker of this session, Professor Rosemary Harris. She's from the Queen's Mary University of London, and her research interest is stochastic non-equilibrium processes. Before you start, I just want to make the announcement that there is a breakout room, which is at the end of the session. If there are question answer session is long, so we can continue there. And for all the participant audience, if there are questions during the talk, kindly ask at the end of the talk, or you write in the chat box and we will take care of it. And over to Rosemary. Yeah, you can start. Yeah, you can start.
Okay, so I'm just sharing my screen. Hopefully it's coming up now. Great, thank you very much for the introduction and for the invitation. I think, like everybody, I'm looking forward to the days when we can return to in-person conferences. But in the meantime, it's a great honor to be with you virtually at this meeting, which I've heard a lot about but never been to. So this is down in the bottom left here. Hopefully you can see my cursor. This is the Maths building at Queen Mary, so you can see where I am now in relation to the centre of London. And today I'm going to tell you about some recent and not quite so recent work on statistical physics with memory, in particular the case of random walks and what they can tell us about modelling decision making. So something perhaps a little bit different to what we've heard so far in this meeting, but I hope at least interesting to some of you. Okay, so let's start very simple, quite early in the morning still in London. So let's start with Markovian random walks. Well, we all know what they are, of course. Let's specialize to the case of one dimension and discrete time. So we have a random walk where the position at time t plus 1 is just the position at time t plus some noise or step length, where these step lengths are IID random variables. And the familiar undergraduate example, we can take step lengths plus 1 with some probability p plus and minus 1 with some probability p minus. And then, of course, we can think of a particle just hopping to nearest neighbours on a one-dimensional lattice with potentially some bias. And this is already a very simple model of decision-making. It's a pretty stupid model of decision-making, but it's a model of repeated decision-making. So we're not talking about kind of big once-in-a-lifetime decisions. We're talking about decisions that you might make many times, whether to have cereal or toast for breakfast, whether to drink Coke or Pepsi. And this one-dimensional random walk you can think of as a model of decision-making where each time you make the decision, you don't remember anything about your previous decisions, you just toss a coin to decide what to do. Maybe a biased coin, but nevertheless a coin with no memory. Okay, so that's the Markov case. Now let's try and be a little bit cleverer and think about non-Markovian things. So adding memory to simple models, even these really simple random walk models, can help us to illuminate some of the general ideas of non-Markovian statistical physics, and there's been various work in that direction, as well as, I hope to convince you today, giving some insight into slightly more realistic decision modelling. But as soon as you say that you're going to do non-Markovian dynamics, then the next question is, well, how? Because there are many different ways to add memory to a Markov process. And here are some of the ones that I've worked on at various points. You can think of having latent variables, hidden Markov models, internal states, or you can think of things like reset or renewal dynamics, which are relevant, of course, for modeling the run and tumble motion of bacteria. But what I'm going to talk about today is something slightly different. It's the class of processes where the step distributions in the random walk, or more generally probabilities or rates, depend on the time average velocity up to that point. So on the whole history of the random walk so far. And within the lens of that class of processes, I want to tell you about two different things. One is some quite technical work on the fluctuation mechanisms that can arise in systems with long-range memory, and this is work with Rob Jack in Cambridge. And then the second, more applied, how studying this class of processes can help us to understand something about decision-making with distorted memory, which is partly some quite old work now from 2015, and then some rather recent developments that I'll tell you about at the end. Okay, so let's start with the first part, the fluctuation mechanisms. And this is really a tale of two elephants, I would call it. There's something which, in physics at least, is known as the elephant random walk. It was introduced in 2004. This is still a random walk in discrete space, just like the Markovian example we started with. But now we have some memory in the following way. If the position divided by time, so the velocity takes a particular value vt, then the next step is right with probability 1 plus avt over 2 and left with probability 1 minus avt over 2. So the memory parameter a controls how your next step depends on what happened in the past. So if a is positive, you're more likely to go in the direction you went in the past, and if a is negative, you're more likely to go in the opposite direction. But always depending on the time average of the velocity over the whole history so far. Elephants never forget, why I think this is called the elephant random walk. And to make things a little bit more concrete, we're going to specialize to the case where the memory parameter is positive, so there's a positive reinforcement. So A will be between 0 and 1. So that's the first elephant model. The second elephant model is something that Rob and I call the Gaussian elephant random walk, GERW, which is very similar, except that the position now is in continuous space. And if the value of the velocity is vt, the next step is from a Gaussian distribution, clues in the name, with mean avt and variance 1. So you see that both of these models have the same mean and the same variance for the next step. But they're slightly different. And what we want to look at now is what their typical behavior looks like, how the memory changes that, and what their fluctuations look like. So let's start with the typical behavior. You can make a slightly heuristic argument in the following way. Supposing that we let delta of vt be the mean displacement for the t plus 1 step, given we've got velocity vt up to the tth step. Then using that function, you can very easily construct a discrete mapping that relates the typical velocity at time t plus 1 to the typical velocity at time t. And then you can look for fixed points in that mapping. You can convince yourself pretty easily that fixed points occur, of course, when the mean distance in the next step, so delta, is the same as your velocity so far. That gives you a condition for fixed points, and as usual with fixed points, you can look at the stability by looking at the slope of this function. And by the usual kind of cobweb construction, you find that if the slope is less than 1, you have a stable fixed point where fluctuations away from the fixed point tend to be followed by a decay back to the fixed point. And if the slope is greater than 1, you have an unstable fixed point where fluctuations away from the fixed point tend to lead to growth away from it. And for both the elephant random walk, the original elephant random walk, and the Gaussian variant, we have the same function delta, just a times the velocity. So it's very easy to see that the fixed point is at 0. And if a is less than 1, it's a stable fixed point. So in the long time limit, the velocity in both of these models converges to 0. That's pretty boring. The question now then is, well, what about fluctuations? How likely are we to see velocities away from 0, and what are the mechanisms that generate them? And that turns out to be different for the two models. And I'm not going to give you the details because it's a little bit technical, but I'm going to focus on summarizing what happens for the case where a is greater than a half. So still less than 1, so we've got a stable fixed point, but relatively strong memory. The original elephant random walk is actually just a Polya-Earn model, so you can use rigorous mathematics and as used, for example, by Francini, and find the asymptotic distribution of the velocity. And many of you will recognize that this has the form of a large deviation principle. It's the exponential of minus some function of the velocity times t. But unlike the large deviation principles that you see in memoryless systems, the rate function, the function of velocity that comes here, is non-analytic in this case. So the memory here has led to this non-analytic rate function. On the other hand, the Gaussian elephant random walk, which looked at first sight rather similar, is in many ways much easier to analyze because everything is Gaussian, and the asymptotic distribution of the velocity is also Gaussian. It's also a large deviation principle. Now everything is analytic, but the power of t has changed. So unlike memoryless processes, where you always see a power of t to the 1 in the large deviation principle, here we've got a different speed. So in this case, the memory has led to a large deviation principle with modified speed, which has been seen in other non-Markovian models too. So why the difference between these two cases? Well, it turns out there are different mechanisms underlying the fluctuations you see. So in the first case, in the elephant random walk case, the mechanism is what we call a long initial excursion. That means there's a sustained period at the beginning of the trajectory where you see high velocities. And that lasts for a macroscopic fraction of the trajectory length. On the other hand, in the Gaussian elephant random walk, what you see is what we call the initial giant leap. You see a very large velocity for a finite number of steps at the beginning, and then a decay with the natural dynamics. Fluctuations always occur at the beginning because it's easier to change the average velocity at the beginning. That's a cheaper thing to do probabilistically. But in the elephant random walk, you've got this fluctuation that's spread over a long time. And in the Gaussian elephant random walk, you've got a very extreme fluctuation, but only over a finite number of time steps. And of course, you can't see this second mechanism for the elephant random walk. And the reason is that for the elephant random walk, the length of each time step, each step the particle makes can't be more than 1. So the maximum velocity is always 1. So the best you can do if you want to have a large velocity is just to have a velocity of 1 for all of your first time steps. And so to have step length 1 for all of the first time steps and then decay. Whereas in the Gaussian elephant random walk, the step lengths can be arbitrarily long. So you can have very large steps at the beginning and then decay. And it turns out these two mechanisms are quite generic, and you can identify conditions for seeing them in different models, also many particle models, and therefore for seeing the effect of memory leading to either a non-analytic rate function or to a modified speed in the rate function. Okay, so that's how we see memory affect fluctuations, at least in this particular class of models. Now on to something a little bit different, but hopefully you'll see eventually a connection. Modeling of decision making. So if we're not just going to make decisions by tossing a coin, how can we do better? How do we make decisions? Well, ideas in this direction go back to the so-called greatest happiness principle of Jeremy Bentham. Here he is at UCL. This is the picture I always used to show of him. Actually, just before the pandemic hit, he moved to a new box at UCL. This is the Student Inquiry Centre, I think, and he sits behind this glass screen. So he left his body to UCL, really his skeleton, really his clothes, stuffed with straw, I think. It's not really his head, which depending on who you listen to is either because his head was so grotesque after the pickling process that they don't dare show it to anybody, or because they had trouble with students from King's College London stealing his head. But at any rate, here's Jeremy Bentham at UCL. And he formulated this so-called greatest happiness principle, the idea that humans make decisions in a way which maximizes their happiness. And that's the sort of forerunner of what modern economists would call utility. You can think of utility very loosely as a measure of the satisfaction, the benefit, the reward you get from making a particular decision. And the idea is that if we're all completely rational, which of course we're not, then we weigh up different decisions and pick the decision with the greatest utility. Now, this is not really quite what happens in practice for many reasons, but one of the reasons is that the utility you think you're going to get from making a decision, the decision utility, is often different from the utility you actually get, the experience utility. And part of the reason for that is because we tend to misremember how things were in the past. So then we have to think about, well, how do humans remember things? And of course, human memory is very complicated, but one heuristic that works well in some situations at least is this so-called peak end rule, which was worked by Daniel Kahneman, who got the Nobel Prize for economics, and collaborators. And it was originally motivated not by happiness and reward, but by experiments on pain, and pain during horrible medical procedures, pain during colonoscopies. So what these guys did was they took a bunch of patients who I'm told had to have colonoscopies anyway, and as the probe was being moved around in their backside, they asked these patients, I think every minute, how horrible is it, how painful is it, and they plotted graphs of pain against time for different patients. And then at the end, they went back to the patients and they said, can you give us one number that summarizes your whole experience? How horrible was the whole experience? And the claim was that this retrospective evaluation could be very well predicted just by taking the mean, the straight average of the worst bit of the experience and what was happening in the last minute or two. That's this peak end rule. In particular, the length of the experience didn't seem to matter too much. People call that duration neglect, but really just the extreme and the end. And they even tested this sort of proactively by leaving the probe inside people longer, but making the last bit only gentle pain, and people went away happier. And I think one of the papers is called something like where more pain is preferred to less. That's a very interesting idea that you can give people some extra pain, but make them happier afterwards. So the aim of what I'm going to tell you about now is to investigate how this kind of distorted memory, and in particular how the memory of the peaks, the extremes, affects future decisions. Not, thankfully, decisions about colonoscopies, but this kind of repeated decision that we talked about at the beginning. So here's the model. It's what economists would call a discrete choice model. I've got a single agent, single person, repeatedly deciding between two choices, which I'll tend to call plus or minus. And we can keep track of the number of times they make each choice up to time t, capital X plus and capital X minus for the number of times they make the minus choice. And of course, as we said, this is just a one-dimensional random walk. And it turns out to be slightly more elegant to consider, instead of the position, the fraction of steps right and the fraction of steps left, or the velocities, with a net velocity that's just the difference, of course, of the velocity right and the velocity left. So far, so boring. Now the new bit, each time the agent makes a choice, each time they go right or they go left, we draw a new utility random variable, u subscript I, which is supposed to encode how the experience was when they made that choice. And it's from some known cumulative distribution function, which may in general be different for the right choices, the plus choices, and for the left choices, the minus choices. And the idea is that the agent doesn't remember this whole string of past utilities. They just remember their maximum utility for the right steps, we'll call u hat plus, and for the left steps, which we'll call u hat minus. The thing to remember is that these things with hats on are the maximum experience for the two different choices. And then it's this memory that we feed into the decision probabilities for the next step. And I use this form of decision probabilities, which economists call logit hopping probabilities, logit decision probabilities. It's related to quorum sensing in other models, and perhaps familiar to physicists because it looks like Boltzmann factors. And the capital T here is a sort of level of noise. So if T is very big, It doesn't really matter what u hat plus and u hat minus are. These probabilities are both going to be approximately half, and you have something that looks like the ordinary random walk. If the noise is very high, you're back to this memoryless case. You're back to not thinking about what happened in the past, just tossing your coin for what happens next. On the other hand, if t is small, then there's a bias in the direction of whichever is bigger, u hat plus or u hat minus. And the question then is, well, how does that affect the long-time dynamics of the model? So let's first think about the case of homogeneous choices, where the distribution of utilities for the right and left steps is the same. F plus of u is f minus of u. Of course, the distributions of the maxima at any given point will be different because they depend on the number of right and left steps you've made so far. So what happens in the long time limit? Well, if you think about it, you might be able to at least speculate that there are two different things that you might see. You might say, okay, well, the problem's symmetric, so I guess if I wait long enough, then asymptotically u hat plus will be the same as u hat minus, and I'll have half of my steps right and half of my steps left, and I'll be in some mixed decision state. So if I make a histogram of the velocities I see in a simulation, then I'll see something that's peaked about 0. On the other hand, perhaps it's possible that at some early point you have a particularly good experience, let's say for one of your right steps, and then you're more likely to go right, and then you're more likely to have an even better experience for your right steps. And maybe you can get sucked into a state where simply by the force of habit, by your early experiences, you become convinced that going right is the only thing to do, and you end up asymptotically in this frozen decision state where you only go right or only go left. And in that case, you'd expect to see a histogram peaked at -1 or +1. And indeed, that's what you see in simulations. You can see both of these things. These are real simulation results. So the question is, well, how does that depend on the noise and on the distribution of the utilities? Well, it turns out you can make a simplified model that allows you to make analytic progress. And the idea is the following. You replace the u hat plus or minus, these maximum experiences, by the so-called characteristic largest values after that number of steps right and left. Characteristic largest value is just the quantity from extreme value theory that tells you if you've had a certain number of trials of a random variable, what typically is the largest realization of the random variable you see. Of course, it's just a quantile defined by the solution of this equation. So if you make this approximation, then p plus and p minus, your probabilities for going right and left, now become deterministic functions of the number of steps right and left, or equivalently of the velocity and time. And now, of course, we're back where we started. We're back with a random walk where the probabilities, or the step lengths, distribution of step lengths, depends on the velocity in the past. This is just a generalized elephant random walker or a Polya-Ern problem. So then you can play all the same games with fixed points and stability to predict what happens in the long time limit. I'm not going to go into the details because I'm conscious my time is moving on. But if you know anything about extreme value theory, it won't surprise you that the prediction is that you find 3 general classes of behavior. If your utility distribution has fat tails, so for example a Pareto distribution, then if you wait long enough, you eventually see something way out in the tails for one of the choices. You're sucked into going that way, you're even more likely to go that way, and you can never escape. So for fat tail distributions, if you wait long enough, you eventually become frozen in one choice, whatever the level of noise. And on the right here, you see simulations of the root mean square of the velocity against noise for increasing times, and they approach 1, meaning that you're either at -1 or +1. On the other hand, if your utility distribution is bounded, a uniform distribution, then if you wait long enough, you'll have seen the maximum for both right steps and left steps, and then you'll be back to an ordinary symmetric random walk, and you sample both choices equally, regardless of the level of noise. The interesting case is the case of exponential tails. And in that case, there really is a transition from a frozen state to a mixed state as you increase the noise, and you can predict the value at which this transition occurs. Okay, so that simplified model has told us that for homogeneous choices with either fat-tailed utilities or exponential utilities with low noise, there's a kind of ergodicity breaking. There's a trapping regime where the time average velocity for a particular agent is either -1 or +1, while the ensemble average velocity is 0. So ergodicity breaking. But it doesn't really matter, because the expected utility in this case is the same for left steps or right steps, so it doesn't really matter what you do, the expected utility for a single agent will always be the same. That changes, of course, if you have heterogeneous choices. Then you really might be trapped in the wrong choice. And this has essentially been the PhD work of this guy, which has very recently been published. So let me tell you about that in the last couple of minutes. So focusing on the exponential distribution, and the case where I have an exponential distribution with mean 1/2 for right steps and mean 1 for left steps, so left is best here. I show you simulations of the utility averaged over time and ensemble for both the simplified model and the full model. And you see that the simplified model looks very similar to the full model, which is great. It means we can try to understand the simplified model to predict what's going on. Simplified model with this characteristic largest value approximation, remember. What do you notice? You notice, well, for noise going to 0, then agents essentially make their first step at random and then get trapped there. So each agent either has a utility of 1 over lambda plus or 1 over lambda minus, averaged over time, and the ensemble average is the mean of these two things, which here is 0.75. On the other hand, for very large noises and finite times, then memory doesn't play a big role. And again, you're sampling both choices equally, and you go back to the same limit. But somewhere in the middle, you've got a peak, somewhere around 1 over lambda plus. And that's the thing that we'd like to understand very briefly. So you can again play this fixed point picture, except that now it's dynamical landscape, everything's moving in time. And very briefly, you predict 3 regimes: a low noise regime, where again you have this trapping, you have this ergodicity breaking. And then in the middle here, an intermediate noise regime, where it turns out there's just enough noise for you to explore the state space and then always be able to escape from the bad choice and end up in the good choice. So as you go to longer and longer times, you eventually saturate at the maximum at 1, and the saturation is t minus 1 with a logarithmic correction. You can show that and check it in simulations. In the high noise regime, well, there's no ergodicity breaking, there's no trapping, but there's a clustering of trajectories around an intermediate trajectory, which moves very slowly towards -1. So also in the high noise regime, you very slowly converge to the maximum, but with a power law, which is much slower, and again, you can predict. But the nice thing is that there's an optimal value of noise for finite times, which gives you this peak, and we can predict that. So I think I'm out of time, but I hope I've convinced you that systems with long-range memory have rich fluctuations, and in particular that this kind of reinforcement memory can lead to trapping, non-ergodicity, and that's important for decision modeling, where an agent can be trapped in the wrong choice, but it turns out there's an optimal level of noise to escape that. Of course, there are many extensions and open questions, which I'm happy to discuss.
Okay. Thank you, Rosemary, for this wonderful talk. And session is open for questions. We can have some quick questions. Are there some questions in the YouTube? Okay, yeah, there is one question.
Okay, I can read that. I think.
Angela, you can tell your question if you are here. You can, shall I read your question or you want to say?
I mean, I can read the question, so I can
Okay,
answer
okay,
it.
okay, okay, fine.
So the question is, are these two mechanisms, large initial extension and initial giant leap, analogous to what you see in sums of IID random variables, where you either have many small deviations or a single jump, even though it's got the big jump principle? Yes, essentially, yes, you can make that link. Yeah. A long question, but the short answer is yes. You have to be a little bit careful how you do it. And here we don't necessarily have IID. You can do things a bit more complicated, but in general, yes. What we want to do, of course, is extensions to many interacting agents, many particle systems, which is much more interesting from the social point of view.
Shraddha, you are muted.
Okay, if there are no more questions, we are moving to the next talk. Thank you, Rosemary, again for this wonderful talk. And yeah, thank you. Thank you. Yeah, our next speaker is Professor Bhautos Vanshal from ISA Kolkata. Are you there?
Yeah, so I'll share my screen.
You can share your screen, yeah. Bhautosh is from ISA Kolkata and his interest is in experimental physics in semiconductor and spectroscopy and many other things. And yeah, he's...
Yeah, okay, so is my screen visible?
Yeah, your screen is visible. You just open your talk. Yeah. Yeah. His topic is critical fluctuation at spinodal singularities. Bhautosh, yeah.
Yeah, so
I'll remind you after 20-22 minutes.
Thanks. Yeah, thanks, Shraddha. So, yeah, firstly, I would thank the organizers, particularly because I'm quite an outsider to the community. So it's very nice to be welcomed. And this is, of course, an experimental talk, which is somewhat out of the theme of the conference, but I hope the topic is of general enough interest. And I've also tried to sort of tweak it a bit to the primarily theory audience. So there might be some slip-ups, so please excuse me for that. And I would really look forward to your feedback. So this is work done by basically it's a part of the PhD thesis of Satyaki Kundu. Let me turn on the camera. And so this is mostly his work, which I'll be presenting. But it's been done with a lot of people, and a lot of theory friends also, and many students over the past few years. And so the main summary is that basically there are many thermally induced abrupt transitions, and many of them are actually found to be necessarily hysteretics, which I'll just describe. And these have very quiet and long-lived metastable states. And what I'll try to sort of show is that these are actually close to physical realizations of the spinodal singularity. And so in that sense, they should actually be considered to be a separate universality class, so to speak, of the mean field type. And so they're critical because they're sort of governed by the dynamics, and the transition is governed by the spinodal singularity. That's what I'll try to sort of argue based on the experimental evidence we've got in a couple of systems. And so part of it has been published, and a lot of the work which I'll be, or at least a small bit of the work, the second half of the talk, is something which we are still sort of working on. And that's more to do with the attractor dynamics and departures from mean field picture, which again, we'll come to that. So just a phenomenon which got me interested quite some time ago, so it's been sort of a peripheral interest for some time, is that, so there are these materials, so vanadium oxide V2O3 is one of such, where you see this abrupt transition. There's this very spectacular change in resistance around 150 Kelvin over many orders of magnitude at a very small temperature window. And what you see is that this transition is always hysteretic. So this is a bit strange if you are used to studying things like semiconductors, where you think that these electronic systems are supposed to be fast. This is not that low a temperature. And what you see is slow dynamics and very peculiar behavior. In particular, you always see hysteresis. And these are things which are known for a very long time. And it's not something that it's that rare either. So there are a lot of materials, for instance, a lot of transition metal oxides, which show this is just the plot of the resistance as a function of temperature. You see that these plots in 3 of these transition metal oxides look very similar. So the underlying physics may be pretty complicated and would differ in details, but the resistance versus temperature shows an abrupt first order transition, and there's a large hysteresis window. And these, of course, hysteresis is supposed to be a dynamical phenomenon, but at least, but these measurements are done under quasi-static conditions on the laboratory timescales, and there is no evidence of, so there is always this minimum hysteresis window which you see. And there are other materials, spin crossover materials, charge density waves, spin density waves. It doesn't matter, just to show there is a whole range of materials which show this nice hysteretic transitions. Manganites, the intermetallics, martensites. Then you have, these are things which chemists have been studied from the 50s. There's this paper by CNR Rao in the late 60s on some alkali, sulfates, nitrates. So you see all of them have this hysteretic transition, and the hysteretic transition is related to an underlying structural transition. So you have a solid state phase transition, which is maybe electronic, would be something else. But because of the coupling of the electronic degrees of freedom to certain lattice degrees, you always have a structural transition. And I guess the point is that the structural transition gives rise to certain strained fields, which are long ranged. And as we know that infinite range Ising model, for instance, is mean field. So if you sort of have a certain range for the interaction, some R dependence, distance dependence for the interaction, then you could get to you can cross over to a different regime of mean field. And in that case, of course, what you'll see is a hysteretic transition. So just to sort of emphasize this point here, this is measurement of the resistance in a different material, Nd and NiO3. And so, of course, the usual understanding of a first order transition is to think of it as a competition between two free energy minima of the minima of the free energy. And the transition is supposed to happen at this point called the binodal point, where the two minima are exactly the same. So this corresponds to nothing really very spectacular supposed to happen. There's a very, very weak mathematical singularity if you really look for it. But basically, physically, nothing's supposed to happen. And as soon as you sort of cross over to a situation where the two minima are not the same in height, then you can get trapped in a metastable state, and then it's a matter of time when it might actually make a transition. And you can enter a stage of extreme metastability, or the edge of metastability is what is called a spinodal, where basically the minimum of the metastable state becomes an inflection point, such that the second derivative of the field with respect to the order parameter also vanishes. So the spinodal of the order parameter is vanishing. So in some sense, it's a critical point, because if I define a susceptibility as the inverse of this, then the susceptibility would diverge. And so just to sort of talk a little bit more about this. So usually one can sort of talk about abrupt transitions as belonging to, so then you can sort of describe them via the delay convention, so to speak. This is what, for instance, catastrophe people sort of call this. And so this delay convention was, of course, what was there in the original van der Waals theory, or any mean field theory, where fluctuations are not sufficient for the system to actually reach the global minimum. Whereas in Maxwell's construction, by fiat, you force the system to always be in the global minimum, the thermodynamic, which corresponds to thermodynamic equilibrium state. So of course, you can always supersaturate a first order transition, because there will be certain energy barriers to nucleation. And of course, just at the binodal point, this nucleation is actually hard. So you always can supersaturate, but the understanding is that that supersaturation would, at some point, the thermal fluctuations, typically when the barrier is something like 10 kBt, 10 times kBt, then the rates, because so there's an attempt frequency, and the attempt frequency is, of course, the microscopic time scales. When you get to something like 10 times the barrier height, then it is expected that under normal statistical physics situations, you should actually transition to the global minimum. So you can see some hysteresis, but the spinodal point is generally thought to be inaccessible because that's too far down, and you can usually never access it at finite temperatures because fluctuations always will always sort of make you cross the barrier, unless there is a certain mechanism which actively suppresses fluctuations. So yeah, okay, so I'm actually not completely going along with the slides. So yeah, so you can sort of think of two mechanisms for a first order transition. So of course, usually you would expect that there is a nucleation, as we said. So there is a height which the system has to sort of cross over, which would be the nucleation barrier. And in the extreme case, you might expect that when the nucleation barrier vanishes, then you get to a regime of spinodal decomposition or continuous ordering, where you essentially have Langevin dynamics describing the evolution of the system. And the spinodal points would actually be corresponding to the situation where you actually hit, where you can approach this inflection point such that the second derivative vanishes and the dynamics slows down considerably. So yeah, so this is what this says. Yeah, so that's what one would expect. So usually you would not expect to reach these two spinodal points. So this is just the cartoon of the free energy as a function of temperature, and as the temperature is yeah, so you would not expect to reach these these two values of free energy, these temperature where these are drawn with the red squares, because the system would not survive in the metastable state until then. Somewhere here itself, when the free energy barrier is some 10 times kBt or something, then you would actually cross over and never reach there. But if you were to reach here, then you would actually hit a critical point. So that's basically the point where the susceptibility would diverge. And just to emphasize that this kind of criticality is actually interesting and somewhat different from the usual second order criticality, which of course corresponds to a phi-4 kind of a potential, so, and which would correspond to the bifurcation language, would correspond to the pitchfork bifurcation. So in both cases, so for here, for instance, the normal form for this bifurcation would be the phi-4 or the x4 potential. And when this coefficient of the square term actually changes sign, then this green curve, as it goes to the pink one, flattens out, and that's what leads to the disappearance of the second derivative and the divergence of the susceptibility. So yeah, so this is what leads to the usual phi-4 criticality. Whereas if we were to sort of find criticality in the spinodal picture, then what is happening is that you have this barrier, and this potential barrier is actually becoming an inflection point like this. And the normal form for this kind of a bifurcation is a phi cubed, or a minus ax plus x cubed kind of a potential. And this corresponds to a more exotic realization of a phi cube of a field theory, which is a phi cubed theory, and the upper critical dimension is 6 in this case, for instance. So I don't think there are any real experimental realizations so far of this. But this is of course being discussed quite a bit. Anyway, so let me just come to our experiments now. So the experiments, basically, so I'll describe experiments on two different systems, this V2O3 and NDNiO3. Both of them are very similar, except this NDNiO3 is, you can think it's a much thinner sample, so the extent of averaging is much less. So it's a very thin film of a few nanometers thickness. So certain features regarding the landscape, which I'll discuss, are only visible on this sample. Otherwise, the physics is very, very similar. The observations are very similar in both these. So yeah, what we're doing is measuring the resistance, and since it's an insulator to metal transitions, the underlying physics is very, very complicated. So let us just use the insulator fraction. So this is basically a metal becoming an insulator as you lower the temperature. So let us take the insulator fraction to be the order parameter. Yeah, just as some kind of scalar, non-conserved order parameter. And then one can say that when one is measuring resistance, then basically you're doing some spatial averaging of this order parameters, like the k is equal to 0 mode of the order parameter is what is measured. So of course you have to correct for some percolation because you're actually measuring the physical resistance, but that's a detail. So in effect, you are essentially measuring the k equal to 0, zeroth Fourier mode of the order parameter in these measurements. And then of course I can attribute certain dynamics, and since it's non-conserved, I can just put in some Langevin dynamics, and yes, this is just the time-dependent Langevin equation of dissipative evolution of the order parameter. So there's a gradient of the free energy with respect to the order parameter. That's kind of the driving force. So at the spinodal, the driving force vanishes, and that's what causes, which is basically the source of the singularity. So yeah, so this is just this depiction of the free energy versus order parameter as your parameter A, which was there in that picture, is changing, and you're approaching the saddle node bifurcation. So I can just plug in, this is usual. So I've just the phi s is the spatially averaged order parameter which I'm writing. So I can just expand my free energy around the spinodal and close to the spinodal. So then I would expect that the free energy would go like this. And if I just plug in to the Langevin equation, then I would have certain expectations for how the phase ordering would be, what the autocorrelation would be, and what the variance of the order parameters would be. So these are the spatially averaged order parameters which I'll be measuring in the experiment. So I see that so all of them actually come with this. So this is, of course, I didn't emphasize, this is just a very hand-waving linear theory analysis. But so of course these exponents would depend on the detail. But the idea that things should diverge is just a consequence of the fact that the free energy is, the second derivative of the free energy is disappearing. And so each one of these taus is essentially related to the isothermal susceptibility, which would diverge with some exponent, which we don't really know. But anyway, so let us try to measure these quantities. So that's what I said. So we are actually measuring the spatially averaged order parameter. And at the spinodal points, if you're really measuring these to be the spinodal points, then we would expect these kind of divergences of the phase ordering times, the autocorrelation times, and the variance of the fluctuations. So let's first discuss these phase ordering experiments. So this actually involves, of course, you can see that this is done in experiments. So and these are essentially quench experiments where you start at some temperature far away from the transition, say 100 K, and then try to sort of shock heat it to a certain target temperature close to the transition. So of course your shock heating is not instantaneous and it's not perfect, but okay, you heat it to some 50 Kelvin per minute. Say that's something which one can accomplish after some effort, and you set it to different target temperatures and then you stay on those. And similarly, you quench cool starting at a high temperature and going down close to the. So at these points, you're basically coming here and here, or coming here and here. So this is the just tracking the order parameter as a function of time, the time evolution, and I can roughly fit a time scale, and you see that it does seem to grow around the two. So of course this is for heating and cooling. The two spinodals are different. So I'll be showing experiments for heating and cooling in parallel completely. So you see that both of them are diverging. And so this does seem to indicate that, yeah. And similarly for NDNIO3 also, you see rise. It's not really a divergence, but you do see a rise around these two, the cooling and the heating spinodals, so to speak. And so now let's come to the fluctuations. So here, what one does is just these are just resistance measurements, and you throw away the actual average and just look at the fluctuation, the resistance, and then you keep, basically you go and sit at a given temperature and just record the time series of resistance over a long period in time, keeping the temperature as constant as you can. And this is what, for instance, some of these degenerate time series will look like. And so again, one can calculate the autocorrelation times of the resistance fluctuations, and these again you see seem to grow both for cooling and for the heating around these two temperatures. And similarly for ND and IO3 also one can see that there's a growth in these autocorrelation times. And so these two things would be critical slowing down. That's what is conventionally called critical slowing down, because there's a critical singularity which is making the response of the system slow. And similarly, the variance of the fluctuations was also predicted to diverge, and that's indeed what you roughly see, that there's a significant growth in the variance for both the systems. Yeah. So in this part, what I've sort of tried to show is that we do see certain evidence for spinodal singularities. In particular, I showed you some evidence for critical slowing down and critical opalescence. So now let's try to see what one can find about the next 5 minutes or so. Let's try to go beyond the naive mean field theory. So in some sense, of course, we are outside of mean field theory because we are looking at fluctuations. But still, most of the things can be sort of understood within simple van der Waals kind of mean field theory. But there is a lot of phenomenology which cannot really be understood based on just these simple ideas. So let me just try to present those. Okay. So maybe let me just skip this part. Yeah. So one of the things, of course, is that so when you're going beyond mean field, so there's a certain finite temperature corrections, and what people have argued is that these finite temperature corrections can actually be thought of in somewhat precise mathematical sense to be somewhat like finite size effects, and they broaden the singularity in the same way. So you may not actually be seeing a true divergence, but the point being that the transition is still controlled by that singularity. But you see certain finite temperature effects very similar to the finite size effects which one sees in simulations, for instance. And more interesting, of course, is what the role of disorder is. And in context of disorder, these systems have been studied quite a bit, but usually in the language of the zero temperature, zero field, random field Ising model. And this may not really directly be relevant because I think that long-range interactions is actually pretty important. Nevertheless, so there's some phenomenology which, of course, has been greatly studied both in theory and experiments, like return point memory, and you can, of course, generate arbitrary phase fractions. These are things which are very difficult to reproduce without putting in disorder or long-range interactions. Or another very weird or strange thing is, or unexpected thing is, that if you look at metastable states deep into the metastable region, which is to say that you can access these metastable states drawing certain minor hysteresis loops. So these states turn out to be very, very quiet. So as sort of indicated by the fluctuation spectra. So the fluctuation spectra of these states, so these are two states at the same temperature. One is at the major hysteresis loop, and this state is the minor hysteresis loop. And these states are actually very, very quiet and virtually indistinguishable from the states in the high temperature and the low temperature phase. So that's actually very strange because these fluctuations, one would expect, are better markers, indicators of the nature of these states. And even for the fluctuations, for instance, the power spectral density of fluctuations, the slope is actually very much like the high temperature, the low temperature phase, is very different from the transition region, and similarly the relaxation times, etc. And what is also interesting is that one just looks at the late stage phase ordering, which is to say that again there are these phase ordering experiments. They start at some low temperature and go and sort of hit this target temperature and wait for a very long time, keeping the temperature fixed, or other way around, starting from high temperature, come and sort of hit one of these temperatures and stay there for a very long time, and then very carefully monitor the fluctuations. So these fluctuations are in the range of 1 part in 1,000 to 1 part in 10,000. So these fluctuations are okay. There's nothing very specific or special about these, except that so in this range of values which are separated by around 1 Kelvin, we see that there's a two special temperatures which are picked up, where you see a clear separation of time scales. So over and above this background, so of course this relaxation is very slow because you also have critical slowing down, but you see a clear separation of time scale, and this kind of this noise which is which indicates some kind of jump between different stable states. And so this seems to sort of, this of course is supposed to be a hallmark of metastability, and it seems to indicate certain attractor dynamics. So of course one can, so it seems that this is some kind of metastability which one really sees, that at these two temperature window around these spinodals, one actually does hit a landscape. So a landscape suddenly materializes where the noise and the sort of the fluctuations, the potential are of similar magnitude, such that you can actually observe this kind of attractor dynamics and in the separation of time scales. And then one can sort of try to characterize this time series. So for instance, the distribution of these residence times seems to show an exponential distribution, and somewhat surprisingly there's no evidence of aging, in the sense this is done over 6-7 hours, whatever, 4-5 hours or more. You can see there's no change in the average residence times or the exit times. And I can try to scale these exit times by the average, and it seems to sort of obey some certain exponential distribution, which is what one would expect. So it's but it's nice that it seems to be just following this exponential distribution without any fitting parameter, except that one would not really expect a single exponential, because one is saying that it's a landscape of wells of different thickness or with different widths or depths. But the point is that it doesn't seem to, at least at the level of the statistics we have of around 10 to the power 3 samples, even if I put in a distribution of so this Anand, Mohan and I were doing together, and so it doesn't seem to really matter that this 10 to the power 3 samples, basically even if you put in a distribution of different exit times or the widths, then you essentially end up with the same thing, and you need something like 10 to the power 5, 10 to the power 6 or more samples to really distinguish between these different points. Okay, so I'll stop here. So if there are any questions or comments.
Okay, thanks Bhavtosh for a nice talk, and session is open for questions. Questions? Okay, I have one question, Bhavtosh. Maybe you have said somewhere I missed. You mentioned about this dynamic exponent somewhere in the critical slowing down slide. What is the value of Z you are getting for this?
So that's very hard. So in the sense, I tried to get something, but the point is that that's not, one can't do it honestly, because these are broadened actually. So ideally you should get something for, so one can't really take these seriously because, these are quite broadened. So one of the ideas I had was to maybe, if you have a field driven transition, then one can try to do it as a function of temperature and try to do something similar to critical finite size scaling to get these exponents, because these are broadened. So I don't think we can get a reliable value.
Okay, thank you. Are there any other questions? Some quick questions. Okay, then thanks, Pautosh, again. And we are moving to the next talk in the list. Yeah, Professor Herbert, are you around?
Yes. Hello.
Yeah, hello. Yeah, thank you.
Okay, so
You can share your screen. Yeah. Yeah, your screen is coming up. Okay. The next talk is from the Professor Herbert Swan. He is a professor of mathematical physics, Technical University Munich, and he will be talking about hydrodynamics of integrable systems, the classical Toda theorem. And over to Professor. Yeah.
Let me see. I first have to do the full screen, right?
Yeah, you do the full screen. Yeah.
Now you can see.
Yeah, thank you. Yeah.
Okay. Okay. So thank you very much for this very kind invitation. I mean, I guess it's a meeting with sort of a variety of topics, and I'm just adding one of them. And let me sort of give as an introductory slide a little bit, what the general framework is. So the way you should think about what I'm trying to tell you is that it's transport in one-dimensional many-body systems. So transport means that I'm going to look at particular time-dependent quantities, and many-body is just sort of a mechanical, physical many-body system. And of course, it's in one space dimension, and that sort of typically raises some questions. I mean, it's unphysical. I mean, one-dimensional systems are not so easily produced in the laboratory. And of course, I mean, that's all correct. On the other side, it's sort of an interesting theoretical playground because, I mean, well, there are various reasons, but one of the most obvious reasons is that, we can still simulate on the computer one-dimensional system much easier than we could do higher dimensions. I mean, I'm talking about time-dependent quantities. I mean, we can do DMRG for quantum systems and the usual sort of molecular dynamics for classical systems with system sizes which in higher dimensions are simply sort of out of scale. And there are interesting theories to check, and this is sort of what I'm trying to tell you. Now, one dimension, in one dimension, you can look at either quantum systems or quantum chains or other quantum systems. Can also look at classical systems. Actually, my talk, I will focus on classical systems because that's sort of, the kind of things which I have worked on mostly. And if you go to one dimension, there's a very peculiar feature that there's sort of, very fine-tuned systems where the system is actually integrable in the sense that you have an extensive number of conservation laws and which sort of, just behaves totally different from the rest. And sort of, that's one of the things which I would try to get across. Okay. So just to make sure that you see that these integrable systems are not purely theoretical and sort of, have some wider impacts, is that I just want to mention sort of the prime system, on which I'm not going to talk, but which is, the famous Liebling delta Bose gas, which are bosons in one dimension with a very short range interactions. And for this, I mean, you have both. I mean, you have interesting theories which are similar to the ones which I'm going to explain. I mean, you can do computer simulations, not so much on the delta Bose gas itself. I mean, continuum quantum particles, even in one dimensions, I mean, it's completely out of scale. I mean, maybe very small systems, but not the ones which, would sort of show interesting sort of large scale behavior. But the computer simulations are needed in order to actually, the theory is somewhat complicated. And if you want to get really data which you can compare with experiments, I mean, you need computer simulations. But for this system, you have sort of quite a variety of experiments. And I'm just sort of recommending this review by by Isabelle Bouchoul and Jerome Dubai. I mean, there you can see the whole spectrum. I mean, it goes from theory to compute, so doing numerical simulations on generalized hydrodynamics and actually comparing with experimental results. Now, it's a wide topic, and it's a short sort of time for presentation. And so what I thought is that it's a general audience. So let me pick sort of one aspect which I always found very intriguing, namely the distinction between many-body integrable and many-body non-integrable. Okay, so the non-integrable case means that you have three conservation laws. I mean, just sort of the standard three conservation laws, whereas integrable you have very many. And I want to do this in the context of one-dimensional classic fluids. But actually, I'm going to use sort of the anharmonic chain approximation because it's sort of theoretically somewhat simpler, and also in terms of numerics, it can simulate larger systems. Okay, so this is sort of what I'm trying to do. And let me see. So there's one slide where I sort of try to explain you the microscopic model. I mean, it's sort of familiar. I mean, you tell this to your students, but let me do it anyhow. I mean, so here you have the Hamiltonians, you have the usual kinetic energy. These are classical particles, and then there is interaction potential where, that's a chain approximation that I only take interaction between the pair Qj and Qj plus 1. So particles are no longer indistinguishable. Okay. Famous examples are the FPU Fermi-Passer-Ulam chain. It's famous because it was one of the first systems which, once computer became available, physicists sort of were curious to understand this many-body dynamics, and then they picked the simplest system, which is if you take the quadratic one, then you have sort of a system which is a harmonic chain, which people have knew for a long time. But then they said, okay, let's take a slightly anharmonic interaction potential, and then the obvious thing is just to put here sort of extra powers like x to the power 4. Okay, so that's the Fermi-Passer-Ulam. Actually, it's for the simulations, it's not so convenient. I mean, the data are pretty noisy. You get much less noisy data. I will show you. If you take the shoulder potential, which is sort of the one which I picked it over here, it's sort of like a hardcore potential, but then I put an extra shoulder. And since I just make the step shoulder, it's numerically particularly easy because, I mean, the momenta are piecewise constant. And so you just have to go from collision to collision, and you can sort of reach, you can more easily average and reach larger system size. Now, amongst the many one-dimensional chains, I mean, there's just one single one. Well, I mean, there's one where I remove the shoulder. That's sort of the hard-rod system, which is a little bit trivial. But there's sort of one really freely interacting integrable system, which is the Toda chain. So that's a very particular fine-tuned potential where you put here just the exponential function. Okay. So all these chains have three conservation laws. One of them is the free volume. I mean, just a difference in between neighboring particles. Then you have momentum because this just depends on the difference. And of course, you have the energy. I mean, which I'm writing down here always the densities. I mean, so this is a stretch density, momentum density, and the energy density, which is simply the sum of the kinetic and potential energy. And you see, I could look at non-equilibrium steady states or maybe domain boundary conditions, but for the purpose of the talk, I do something which is sort of extremely well defined. I mean, which sort of prime goal of the theory. Namely, I just imagine that I can ideally prepare a thermal equilibrium, which is this particular sort of canonical distribution, and I put the average momentum equal to 0, so you have something like the inverse temperature. And in order to confine the system, I mean, you need some external pressure. I mean, this is this external pressure term, which is here in the canonical way of writing it. Okay, so the pressure is sort of the dual to the free volume. And if you press the system very hard, then it's a little bit strange for this Toda chain. But what happens is that usually particles are ordered like 1, 2, 3, 4. And if I press the system too hard, I mean, then it will sort of, punish me, and it will get, and the particles will get actually anti-ordered. All right. So here are these equilibrium time correlations. I mean, you know, the equilibrium distribution is time independent, it's stationary in time, and it's also stationary under translations. And therefore, I'm going to look at the correlation, let's say, between the stretch, I mean, the stretch at time t and lattice point or particle label j, and the same quantity at 0. Typically, such quantities will not decay to 0, so maybe I should subtract the average. I mean, that's a C, and then, of course, I have to remember that depends on the thermodynamic parameters, which are beta and p. So of course, I can replace, you know, this observable by the other ones, I mean, by the momentum and energy, and so in fact, I get sort of a 3x3 matrix, 3x3 correlator of physical interest. Okay. Now let's look at this. I will show you some numerical results, but to show you, I just want to give you the overall picture what you're going to see. Namely, if I take a non-integral case, so like the FPU or the shoulder potential, then you will see sort of three comes because there's three conservation laws, three sharp peaks. And they have some symmetry. I mean, one is sitting at the origin, that's the heat peak, and then you have two sound peaks, which are sort of moving outwards ballistically with the sound speed, which I call here C. Okay. Now, then you say, okay, what is interesting? Well, I mean, interesting is that, of course, you know, these peaks have an intrinsic structure. I mean, you know, they have a shape function. So here I put the shape functions, I mean, which are governed by these exponents alpha and gamma. So this is the heat, and these are the sound peaks are symmetric. So there's just one shape function for the sound. And of course, one goal of the theory is to predict the shape functions and to figure out what these exponents are, and to compare this with numerical simulations. And when you go now from the non-integrable, the generic non-integral case to the integral case, you will see a totally different picture. I mean, you know, basically what you see is sort of like an infinite number of peaks. And so this eventually combines into a broad ballistic spectrum. So there are no peaks anymore. It's just sort of some broad structure which scales ballistically. I mean, so, you know, this is what I've written over here. It's just the shape function is just a function of x over t. Now, of course, you know, there are longer time effects, and then, you know, the picture itself sort of is more complicated. But I just want to concentrate on the ballistic scale here. All right, so this is what we should see. And so now let me show you some numerical plots. So here you see the FPU chain, I mean the FPU fluid, and you see here the heat peak, which is sort of broadening, and you see here at 3 different times the sound peak, which is sort of moving out ballistically, and it's also broadening in a self-similar way. And now we look more precisely at the structure of the peaks, and what you're going to see is, first of all, I showed you here the peak in the middle. I mean, so these are at 3 different times. The dotted line is sort of the prediction, and you see already that, you know, there's the alpha exponent, which I put is equal to 0.5, and you see sort of reasonably scaling. Okay, so let me show you the other one. That's the Carda-Parisi Sang peak. I mean, I will explain a little bit, you know, why it's sort of connected with Carda-Parisi and Sang. But you see, it's not completely perfect. It's a little bit shifted, and it has a different scaling exponent, which is 2/3. Okay. Now I want to show you the same thing for the hard rod, and basically what you should see is that, first of all, you know, it's universal behavior in the sense, you know, it looks the same as for the FPU, but I get much better scaling data. In particular, I mean, you can see, you know, that there's a really very nice tail sort of, you know, out here, which I will explain you in a second. Of course, the exponents are the same. There is only one single fitting parameter in this data. I mean, it's this 3-parameter lambda, which is fitted. Okay, so here you see the KPC peak, and since you can hardly see the difference between theory and prediction, you know, I put here a logarithmic scale, which is just the same thing plotted, but on a logarithmic scale, and there you can sort of see it more clearly. This one is sort of the prediction which comes from the KPC equation. And you see that, you know, out here, I mean, things become noisy, so I cannot really compare. And you would be tempted to say that this must be a quadratic function. Well, it's very close to quadratic, but when you do a more precise fitting, then you see that, you know, at that level of precision, it's no longer a quadratic function. I mean, the shape function is not a Gaussian, it's a different function. All right, so now, so this were the pictures for the non-integrable case, and now I want to contrast this with the pictures from the integrable case. So here you see the integrable case, you see this broad peak, this is the stretch correlation, and I want just to see the precision. I mean, this is only at two different times, and I mean, now we have better pictures, but anyway, I mean, it just gives you an idea that, you know, the errors of order 10 to the minus 2 roughly all the way through. And if I look at the other correlation functions, of course, they are different. So, you know, this just stretch a little bit, and then here they are yet different. But it's always the same. I mean, there's, you know, it scales ballistically. Okay. And so now I want to sort of explain you a little bit what is the theory behind it. And let me make one slide on the non-integrable case. I mean, this is something which you can beat. I mean, I've written these Lesouche lectures where these things are discussed at great lengths. And the result of the theory is that there are three universality classes. And I'll just show you the generic one. And for the heat peak, the prediction is that it's more easy to write this in Fourier space. So, you know, the prediction is what people call the Levy distribution. So it's sort of like a Gaussian, but you have here this exponent 5/3. And because you have the singularity at k equals 0, it's k absolute value. When you go to real space, I mean, you will see these long tails. I mean, this is what I try to point out. I mean, and of course, this distribution has a name. It comes from stable laws, and it's called the Levy distribution. Okay. Now, for the sound peak, you find this what people call the KPC function, which has this 2/3 scaling, and which was sort of originally obtained old work by Brehoff and myself, but later on I made a huge amount of work afterwards, and we have sort of exact solutions, all kind of things. Anyway, so let me just explain you where the name KPC comes from. So the observation is when you look at the Carter-Parisi sum equation, and if you just take one spatial derivative, you get something which is called the stochastic Burgers equation, which has a very sort of generic structure. I mean, it's a conservation law. It's ddt of u. U is just a scalar quantity. It depends on x and t, and it has sort of this conservation of some current. And the current has three pieces. It has a nonlinearity, so that makes the equation sort of somewhat complicated. There's a diffusive term which sort of, you know, smoothens things, and then there is space-time white noise. So this depends on x and t, is totally uncorrelated. Okay. And now the claim is that if I want to get a theoretical prediction of the sound peak, what I should do is I should simply look at this scalar equation and compute its stationary space-time correlator. So the average is 0, and you have to compute this correlator. And this is somehow what we did in this paper. I mean, you can actually find an exact solution. Now, of course, this solution is not yet scale invariant. So then you have to take long time limits, and then you get sort of, you know, what would be the theoretical prediction for large scales. And the scaling function has a formula, and we denoted it by KPC because it's based on the solution of the KPC equation. And when you look more carefully at your numerics, I mean, you find that you know, it has to decay like e to the minus x cubed. So the tails are not quadratic, but sort of, you know, slightly faster decay. All right, so that's very, very briefly the non-integrable case. And now let me show you, as a contrast, what happens in the integrable case. Okay. Now, basically, the idea of the integrable case is that you can still do the Landau-Lifshitz theory. You see, for the non-integrable case, the Landau-Lifshitz theory would give you just simply wrong results. I mean, so you have to go to higher orders, to non-linearities in your hydrodynamic equation. But the claim is that for the integrable systems, you don't have to do that, but you have another difficulty because you have now so many conserved quantities. I mean, you know, your conservation law will not be just simply labeled by 0, 1, 2, but, you know, this series just continues. And if I go to large scales, I mean, you know, this will become sort of like an infinite series. I mean, it's discrete, but, you know, it just goes further and further. And so I will have an infinite coupled set of nonlinear hyperbolic conservation laws. But, you know, the philosophy is the same. If I want to compute these correlations, I will look at small deviations from equilibrium, so I can sort of linearize this equation. And that has the advantage that I get now a linear equation, but this will be essentially sort of a high dimensional matrix. But it's now just a background, so it's independent of x and t, and I just have to solve this linear equation, which formally, of course, I can easily do. Formally, I can easily do because I put this just up with the exponential. Here you see the ddx, and here you see this infinite matrix. And because I'm computing time correlation functions, what I have to do is I have to act with this thing again on another infinite dimensional matrix, which is the static correlator, which is sort of delta correlated in x. But you have all the components, so it's still an infinite dimensional sort of a large matrix. Okay, so I mean, it's nice to write down the formula, but of course you have no idea how to do it. I mean, how would you compute, the C matrix? How would you do the A? I mean, so unfortunately, I cannot sort of go into any details of here how to do that. But I want to explain you one key physical idea, which I find sort of very intriguing. It's sort of I can explain this without actually going into the details of the formulas. I just want to say that all these matrices are fully occupied. I mean, you cannot just sort of cut them down to 3x3 matrices. I mean, you will get just totally wrong results. Okay, so now let's see what I want to explain. This is this Lex Matrix Filter. Okay, so for this I have to give you one slide on how people sort of figured out how to solve the total lattice. I mean, this goes back to the 70s, and you introduce new variables which are called this HA, which is sort of the square root of the potential, which is this particular. And then in these new variables, I mean, your equations of motion look very algebraic. I mean, they look much simpler. You see the dDTA, I have just some nonlinearity on the right, and the dDT of the momentum has a quadratic function on the right. So somehow, the algebraic structure becomes very easy. And there is this absolutely amazing fact that, this can be written in terms of the evolution of a matrix. I mean, this is called the Lex matrix, which is diagonal along, it's tri-diagonal along the main matrix. You have just the momenta, and then these Flaschka variables you are just on the off diagonal, and this comes from the periodic boundary conditions. And what you find is that there are some other matrix which is actually completely unimportant for that purpose. For my purpose here, is that you can write this in terms of the evolution equation of a matrix. So this T becomes time dependent because I'm solving the total lattice equations, but then its time derivative can be written as a commutator. And from this, you conclude immediately that the eigenvalues of the Lex matrix are time independent. And so, I have sort of an algebraic way of constructing the conserved quantities, which are, of course, very complicated functions, and they are also non-local. And if you want to make them local, it's better actually to look at the traces of this matrix. So if I look at the m's trace, I mean, that is sort of typically that is a conserved quantity, and the lowest order, I mean, n equals 0, 1, 2 are the standard conserved quantities. I mean, the stretch, momentum, and density. And so this simply gives a sort of a tower of higher conserved quantities which have no names and which sort of are not really interesting per se. I mean, it just help you in order to do the analysis. Now, the central observable, and this is why I'm putting up the slide. I mean, the quantity which sort of the slowly varying quantities happen to be the density of states. So the density of states is a quantity which simply, gives you the distribution of eigenvalues, just what you sort of know from quantum mechanics. And of course, this is a random quantity, but it will become self-averaging in the Gibbs ensemble. So, for large system, you should think that, this sort of converges to a smooth function with very, very little fluctuations. And what I want to show you is that it's that quantity for which you can write down a hydrodynamic equation. And let me show you this in terms of a picture. So here I have sort of my system, and I break it up into little cells. I mean, let's say 300 by 300. I mean, that's sort of arbitrary, just for the example, and should be not too small. And now I go 1 times that. Again, the 1, I mean, you should not take too serious. It's just for presentation. But what I want to emphasize is that now you have a local Lex matrix. You see, I take 300 size, I just construct my 300 by 300 matrix, and out of this I can make spectral density. I can look at the density of states of, in this little block. And now I can go to the neighboring block, and I assume that initially I put things that, this doesn't change so much from one block to the neighboring block and can get a neighboring block, etc. But I can also look at the same thing in time. And now the claim is that this local density of states is actually slowly varying on the ballistic scale. You see, they're not so noisy anymore because, they're self-averaging. I mean, they don't have sort of wild fluctuations, but, they are rather smoothly varying. And therefore, you can hope that you can actually write down an equation for this kind of quantity. And lo and behold, that's actually true. And the equation, of course, has now again sort of the form of a conservation, or it's ddt and dx here. But you have then this extra sort of parameter for the density of states, and then here you have space-time, and here you have space-time. Here's the density, I mean the Lex DOS, and here you have the corresponding current. Okay. And of course, this equation by itself is totally useless unless you know what the current is. And so the current, of course, you must have a closed equation, must be a functional of the rho itself. And how to do this, that's a difficult thing. And this was sort of observed, invented 2016, and by now sort of, applied to many systems. So in some sense, we know very well how to do this for, any integrable system you tell me. I mean, maybe not quite as any, but pretty much. Okay. And so now let me show you no, let me see. I skipped one thing which is important for the discussion here. I wanted to give you the idea of the ideal gas. See, for the ideal gas, these carbons are just proportional to the density times the velocity. And then, of course, these things decouple and you get a very simple set of equations. But here, everything couples. And of course, this functional will be much more complicated than the one which I have here. So let me just show you sort of that you get a feeling for when I talk about comparing with theory, I mean, what do I mean, right? And so let me just sort of state without any further explanation, what is the result of the total lattice. So here I've written down this correlation function, which depends on x and t. And basically, I'm summing here of an infinite number of modes. I mean, you see, this is x, and there's some velocity here times t, okay? And then, of course, w goes over r, so I have an infinite number of modes. They all have their own velocity. And then I have to do a weighting. I mean, the weighting is the density of states of the underlying Gibbs distribution. So that's something which you have to somehow figure out what it is. And then, of course, there must be something which gives you, the physical observable. I mean, this is what is coming over here, okay? And unfortunately, the best is not so easy, but I just sort of, in order that you can have a look, I mean, you have to do this stressing transformation, which is sort of, written down here, and you have to compute this effective velocity, which is written down here. And, everything involves inverting sort of an operator, but the most important message which I sort of want to transmit is that, independent of this particular sort of integral equations which you have to solve, you wonder where is the dynamics of my total system. Everything sort of looks like, of course, it has to enter somewhere in the definition of this effective velocity, but how does it enter? And now, what you somehow might have expected, but this was at the time was a real surprise, is that essentially all what is left over from the dynamics is the two-particle scattering shift. And two-particle scattering shift is here this logarithmic function, and it's this T operator which as kernel has the two-particle scattering shift. And this is sort of a universal property. If I would do the delta Bose gas, then I would have to do the scattering shift of the delta Bose. If it would be a quantum system, it looks slightly different, but essentially it's the same type of formulas. Okay, but when I talk about comparison, I mean that we do a numerical simulation of the total lattice, and then we do another numerical simulation which figures out all these integrals, which gives you then an explicit theoretical function, and then we do the comparison. So this is the picture which I showed you. I mean, there were two types of very different simulations. One of them actually figuring out what this function is, and the other one doing the full microscopic dynamics. So I guess my time is over. And so let me just say that if you want to have more information, there are these two sort of lecture notes, and also I've written some notes which are still in production, but you can find it on the archive. And there are two special volumes which you can look up. And thank you very much for listening.
Thank you, Herbert, for interesting talk, and the session is open for questions. I'm sure. Yeah.
Let's see. Yes, so now I'm. Okay, now I'm back. Okay.
Yeah. Questions.
So at the beginning, you talked about this FU model, and the FU potential can be replaced by a state potential, and that helps. Can you explain that better?
No, but I didn't sorry, I didn't get the question. I mean, so yes, about the FPU model. I mean, what did you want to know?
So the FU potential, you replaced it by some kind of state potential, and you said that the noise what you get in FU model is reduced by doing that.
The solder potential you were talking, solder one.
I was talking about, sorry, I mean, so I was talking about...
Solder potential.
So I was talking about the TODA or the FPU. Which one do you want? The TODA or the FPU potential? FPU. Well, FPU is just sort of an anharmonic potential. And of course, you know, I mean, you have parameters, you have to somehow do the parameters and look at, you know, how it depends on these parameters. I mean, we have done simulations for various parameter ranges. If you go to very, very low temperatures, I mean, what was the original sort of, you know, idea of Fermi-Passer-Ulam, then you will not see anything of the feature which I showed you because, you know, it's too low a temperature and you're very close to an integrable limit. And so, yeah, okay, I'm not sure whether I'm answering your question, but
no, you replaced this FU potential by a shoulder potential.
The shoulder potential, yes.
How does it help? How does it help?
Well, I mean, the shoulder potential is the one which I showed you. I mean, it's just the shoulder, and you do exactly the same thing. I mean, you simulate basically from collision to collision. You know, whenever a particle comes to the shoulder, there will be an instantaneous change of the momentum, right? And so your numerical simulation just means that you're taking, you know, you do free motion of your particles, and then there's sort of an algorithm which sort of picks you know, what is the next collision. And once you do the collision, it's instantaneous. I mean, so you just sort of do the updating, and then you go from collision to collision, and that's sort of, you know, I mean, it's you know, you can simulate larger system than when you do the FPU, where you have to solve the differential equations. So that's the idea behind the TODA, and it comes out actually, you know, I showed you the picture. It comes out that actually the shoulder is very good. I mean, there's another system of a similar quality. You can take, you really point particles, but you can take alternating masses. That also makes the system non-integrable, and again, you get very good data.
Okay. Thank you.
Okay, sorry, I didn't get the question. Okay.
Okay, thank you, Herbert, and thank you for your interesting talk.
You're most welcome.
Yeah, thank you. We are moving to our next speaker for talk in this session, Professor Supriya Krishnamurthy. Yeah, Supriya. Yeah.
Yes.
Stockholm University, and her research interest is non-equilibrium statistical mechanics. Yeah, you can share your slide.
Yeah, okay, so sorry, there was something that went wrong. Yes, I think I have to go back to entire screen again.
Yeah, you have to go back to your entire screen.
Yeah,
but first you have to present
yes.
your screen.
Yes, and I'm doing that now.
Okay.
I hope you can see it.
Okay, it's coming. Yeah.
Yeah.
Yeah, now you are sharing your screen. You have to open your talk. Yeah, it's coming. Okay.
Yeah, can you see that? Yeah. Okay, so now I'm going to do full
now
screen.
You can start. So Supriya is talking about quantitative analysis of non-equilibrium system from experimental data. Over to Supriya. Start.
Yeah, so you can sort of see this and you can hear me too, right?
Yes, it was there, but it is gone. So can you go back to the...
you have to again open it. It was there.
Yeah, click on that page.
Yeah. I don't know why it went to
you leave it like this. You just click on that file.
Yeah, can you see it now?
Yes.
Yeah.
Now it's fine.
Great, and let me just check that I can. Yeah,
it's working.
Great, so now you can see it and you can hear me too.
Thank you.
Yeah, so yes, so thanks to the organizers for putting together such a great meeting and for giving me the opportunity to talk here. Like many of the speakers said before, the best would have been if we could be there in person, meeting you all, and in my case, eating also those sweets, Calcutta sweets that I really like. But the next best thing, if that's not possible, the next best thing is that we meet this way. So thanks again. I've changed the title a little bit from what I gave you all, but I think the content of the talk is not very different from the abstract I sent. So I hope that's okay. Okay, so I guess the only part of the title which I should explain a bit is what exactly I mean by quantitative analysis. And so I'll get to that. But before that, I should say that this was work done by Shrikant when he was a PhD student with me. So that was, he finished in 2020. And now he's a postdoc at Nordita. And, there are many sort of ramifications that we are continuing with. We also had other collaborators. So in some of these papers mentioned here, Deepak Gupta, who many of you know, and then Shun Utsubo and Takahiro Sagawa in Japan. And then more recently, and I'll get to that at the end of the talk, is this collaboration we have with Oyon's group in ICER Calcutta. So this is sort of maybe appropriate place to talk about that too. Okay, so yeah, so basically, I can see my presentation. I can't see any of you, but I hope that we, if there's anything that you would like to ask and so on, we can do that in the breakout rooms later. So I can't really keep track of either the chat or the, raised hands, etc. Okay, so what exactly do I mean by quantitative? So basically, so the idea is this, that you have some system and you'd like to understand it. It's maybe not some system that you have a model for. Okay, so it's something that you're interested in, but you don't have a model for that. And maybe all that you have is experimental data. So from this experimental data, sort of what kind of understanding, quantitative understanding that you can build up about the system. So that's basically what it means. And this thing has become quite interesting again now for reasons that, now you can do quite amazing experiments with all kinds of things with, sort of nanometer and microscale objects and so on. So for that reason, even though many of the ideas are, old, sort of, it's become sort of interesting again in the context of looking at them again in the context of experiments. So one aspect of this quantitative thing is, can you detect that the system is out of equilibrium? Okay, so you might say, isn't it obvious that it's out of equilibrium? But it's not quite that obvious when it's a really tiny system. Like this little thing that I've shown you here. Can you see my cursor if I move it around there?
Yes.
Great. Okay, thank you. So this little thing here, that's a little green algae called a Chlamydomonas. And these people, whose paper I've cited here and at the bottom, they did quite an amazing experiment. They sort of took a look at this thing and they took a look at its sort of fluctuating flagella. And, just looking at it, you can't quite say, it's equilibrium, it's not equilibrium. I mean, the Chlamydomonas may be able to say, but we don't know. But what they did then was that they sort of plotted it in the space of these, so they broke, they projected these, shape fluctuations in the space of these three first bending modes of a flexible rod. And in that three-dimensional space, they can actually see, you can see here this probability current in this phase space of these three modes. And this is all, experimentally obtained about this system. So there is a probability current in the phase space of the system. Okay, so that means that the system is out of equilibrium. So and that's something, of course, that we know. So basically, this broken detail balance, there are, of course, other ways that have been suggested to understand it. Besides actually mapping out the current in phase space, there are several other interesting areas. Interesting suggestions. And as I said, it's not that it was not known before, It's just that now this application to these, this experiments is a bit new. Okay, so another way that people have thought about, sort of quantifying that, or at least detecting that the system is out of equilibrium, is the violation of fluctuation dissipation. In equilibrium, this quantity, sort of the spectral response and correlation functions should be sort of, when properly scaled with the temperature, should actually lie on top of each other. And the fact that they don't, so this one is the sort of response, sorry, these are the correlations, this is the response, and you see at some low omega, they are not lying on top of each other, and that is sort of an indication that the system is out of equilibrium. And this is again experimentally done. Another way that people have looked at it is these waiting time distributions. So we heard a little bit about these residence times in the talk earlier, but these people have looked at is that if I have some sort of access, if I know that the system is in a state A, that A, of course, could be a mix of, a bunch of microstates that I'm not able to access, but at least I know that there is this broad category of states that I can call A, and then another one B, and then I can look at the waiting time distributions experimentally determined, and then whether it's, monotonically decreasing or non-monotonic gives me an indication of whether it's out of equilibrium or not. Okay, it's one of those conditions which is if this exists, then the system is not in equilibrium. If there's a non-monotonicity in the waiting time distribution, okay, fine, then the system is not in equilibrium. But the reverse doesn't necessarily imply. So I could have non-equilibrium systems where this doesn't happen too. Then there are even others. So when you're talking of detecting a system which is out of equilibrium, there was a very recent paper on the archive that talks about spectral densities of trajectories measured in a certain way, the symmetry or the asymmetry of this points to the thing being in equilibrium or not. In this particular case, it's a bit unclear, how general this prescription is, since they applied it to a very specific model. But in any case, it's an interesting suggestion. There is also a paper by Satya and his student Francesco Mori and Gregory Scher, where they look at a 1D system, and then they say that if they look at the distribution of the time of the maxima, that's either symmetric or that's not symmetric, and then that points to whether the system is in equilibrium or not. So there are all these interesting suggestions for getting the data, so sort of time series data from an experiment, and then assessing whether a system is in equilibrium or not. And then you could ask, can we get more quantitative than that? Can we talk about how out of equilibrium the system is, sort of not just is it or not? Can we talk about how out of equilibrium a system is? And there a very sort of obvious quantity to look at is this entropy production of the system. And in fact, each of those cases I mentioned here that detect whether a system is out of equilibrium or not, either exactly give this entropy production in some way, or they are actually giving some bounds on the entropy production. So the only one that I don't know is this extremal statistics. I don't know if there's any connection to entropy production for this particular case, but in every other case, there is definitely one. Okay, so this entropy production is something, I'm sorry, there are many experts in the audience, many of you who know this much better. So I'm just, but I just thought just for completeness, I should say this anyway. So, of course, in equilibrium, everything can be assigned an entropy, but a system is not producing more entropy, okay? So that's not increasing the entropy of the universe. On the other hand, when a system, when I have a machine, for example, which is not in equilibrium, because I can work it between two reservoirs, then of course it's producing entropy per cycle, so which is just this familiar expression that we know. And if this system at the end of the cycle also had some internal changes which caused its entropy to change, that's something I'd have to add here. In an exactly analogous manner, I can talk about entropy production in small systems too. And here is a sort of a colloidal particle in a 2D trap, and its phase space is just the two-dimensional space, and we'll mention it briefly a little bit later. So it's called a Brownian gyrator, but it's also called by different names, bead spring model, and so on. So in this particular case, it's kept out of equilibrium by two different temperatures on two different axes. And there is a, within the sort of framework of stochastic thermodynamics, you can assign entropies to trajectories. And then, and when you do that, then the average expression for that gives you back the familiar expressions from the macroscopics. However, now you not only have access, or you can not only measure averages, you can also talk about higher moments, variances, and so on. So that will also be interesting for us a bit later. Okay, so so it's consistent. So these ways to define entropies from sort of trajectories is consistent in the sense that it goes back to, so for example, if we sort of model this by a Langevin, overdamped Langevin process, then it keeps with our intuition of how dissipation occurs in this. Anytime I force the system, it's an overdamped system. All the forcing is dissipated as heat in the medium. So it is a sort of a consistent way which keeps with our intuition on what entropy production should be. So we talk of entropy production or entropy production rate. Okay, so the sigma, which will often appear, is an entropy production rate. Okay, so there's an entirely consistent way to do this for finite state space or infinite state space systems, but in the interest of time, let me just talk about finite state space systems. So if I, so this is stuff that you all know. If I have detailed balance, then if I'm looking at transitions between B and C, then this ratio of this to this is actually just 1. But if I'm not in equilibrium, there is this phase space current. And then the ratio of this can be defined as E to the sort of total entropy production per bond. Okay, so, and then if I average this in some way over a trajectory, which I'll get to, then I get my, total entropy production or entropy production rate of the system. And this can be done equivalently for continuous state space systems also, but in the interest of time, let me just not do that. And let me just talk a little bit about the focus of what we started out with. Can we get this from data? Okay, so maybe it's not a system I have any model for, I don't know. So can we get this quantity? So just like all talking about, can we get can we just understand if the system is in equilibrium or not from the data? Can we get this entropy production rate from the data? And you can. So for example, let's say we have our 3-state system, and I'm able to identify these states A, B, and C, and there are transitions between them. And I have this very, 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 sort of long time series of these transitions, A, B, C, etc. So basically, I let the system reach steady state. So I should say that, most of the talk is about non-equilibrium systems in steady state, unless otherwise mentioned. So I let the system reach steady state. So I expect that this entropy production rate has one value, and that's that one value that I want. Okay. So basically, I keep track of transitions. So if I just concentrate on BC, then I keep track of all the transitions there. I multiply it by this quantity. Sorry, I should have. So this quantity here, this ratio of PB, WBC. So let me call this FBC. So I multiply. So this current that I get from the data, I multiply it by this quantity. And if I have good amount of data, then and I do this for all the transitions, then I get this average entropy production. And then if I divide it by the time of the trajectory, I get a rate. Okay, so this is a current, but sort of abusing a bit of the notation, we'll call this whole thing also a sort of current or a generalized current. Okay, a bit later in the talk. Okay, so this is a sort of way, within the framework of stochastic thermodynamics, given, some assumptions that you define, per trajectory and entropy production, and there you can get the average, and you can also get the variances or higher moments. And but it's not the only way, of course. So there are several other ways that are known. I forgot to mention that this kind of idea that this should be equal to E to the something which is equal to the entropy production per link or per set of states is of course quite an old it's quite an old idea, I guess, going back to work of Lebowitz and Spohn from more than 20 years back. So as you see, trying to do it this way is quite intensive, data intensive. You need a fair amount of data, because essentially what are you doing? You want to get the steady state from the data. You want to get all the transitions from the data. So basically that's what you need. So there are other ways suggested too, again, with the interest now that you can actually do these experiments and check. So one is this Kullback-Leibler divergence. You can get probabilities of forward and backward trajectories. And this K is, how many variables in the phase space are you able to keep track of? So the more you keep track of, the more likely you're to be close to the sort of the full entropy production. The less you keep track of, the lower the bound it is on the total entropy reduction. So that's one. There's the other one. So related here, if you mentioned this, fluctuation dissipation violation. So there is this Harada-Sasa equality, which relates, in fact, entropy production to the amount that you violate this fluctuation dissipation relation. And these are very popular and have been checked out on several, experiments, experimental data. There's also this Langevin equation reconstruction, which is also interesting. And again, it's an old idea, which sort of has become interesting again now. And that is that, if I know that my system is sort of modeled by some kind of like overdamped Langevin equation or whatever, then can I sort of, just from the data reconstruct, the drift and diffusion parameters and so on. And if I'm able to do that, and then, from there I can get this entropy production too for the system. Okay, but the thing that is interest to us is this thing called the thermodynamic uncertainty relation, which was what Shrikant worked on in his PhD. So basically, this thermodynamic uncertainty relation is sort of was introduced by Barato and Seifert in 2015. And what they notice is that if I take this, this fancy J here, which is this generalized current in the system, which maybe I just, can calculate from the data. Then the variance upon the mean square, okay, multiplied by the entropy production of the system. So sigma into tau gives the entropy production of the system for a trajectory of length tau. It always satisfies this inequality. Okay, so that's the TUR. And and so initially, it was very interesting because they thought that maybe this is going to be, maybe I can, sort of by knowing this, sigma or sigma tau, I'm able to actually say something about fluctuations of currents. But then it was realized that the other aspect is also interesting. So that if I know the fluctuation of currents and so on from the data, then I'm able to actually put a bound on my dissipation in the system. Okay, so that's yet another way of being quantitative about a system that you don't know. You get this data, you measure all the stuff that is here on the right, and then you bound your sigma. Okay, so there are many aspects of this which are interesting. However, what was realized is that this tau, so typically if this tau is very large, you don't get a very good bound. So let me just miss all that stuff. So if you go back to our Brownian gyrator, the little colloidal particle in 2D that I showed you, and you just take a look at this, this is our estimate for so forget about all these other, and just look at this sort of dashed blue line maybe. And this is our estimate of the entropy production. And this is, the length of, so basically I have a very long trajectory and I chop it into segments of length tau. And then I calculate the variance and the means of the currents over those segments of length tau. And then you see that the longer the tau is, the worse the bound is. The true entropy production of the system is up there, that line. Okay, it's a steady state system, so it has one value for that. But the longer the tau is, the worse the bound is. And then so what we realize is that if we can actually reduce this tau, so you actually chop up your very long trajectory into tiny elements, in the limit tau going to 0, you actually get the exact entropy production rate. So that's what we call the short time TUR. So maybe just in a couple of minutes, let me just explain, so because we talked of, the brute force way to get it from the data, here's another way to get it from the data. I have this very, very long, so I have a steady state system, and I have this very, very, very long sort of time series. I chop it up into, very short time series. And when I do that, I calculate the average and variance of this J, this current, which I defined over these short segments. Okay, and then I get this generalized current. This will give us some estimate. And I vary the weight function. So because you could say, I shouldn't use any information about the system, that would be cheating. But what one can do is, since we know that the maximum of that ratio is what gives me the entropy production, I can vary this weight function using some numerical algorithm for that, and then the maximum gives me the best estimate. And so, and what we found is actually that it works also for transient systems, so we can actually get a time-dependent entropy production. It works for overdamped Langevin systems, and for discrete space, state space systems, you have to modify this expression here a bit, but it works there too. As I said, you can talk about a lot of things, but when you actually apply it to experiments, then it's a whole new thing altogether. And we were very interested to understand if that scheme actually works on experimental systems. And so we had this collaboration from which we learned a lot with Ayan Banerjee's group at StatPhys Kolkata and his students, Shubro, Avijit, and Biswajit, and Dhrubaditya Mitra, who's here at Nordita, and his student Vipin were also involved, and of course Shrikant. So in this we actually looked at a colloidal particle system for which we knew the analytical solution, and then applied the scheme of this short time thermodynamic uncertainty relation to that, and we showed that you can kind of get the right answer. So of course, we learned a lot of stuff when we looked at all this experimental data. I would say it's in some aspects quite a challenge, because you never know what you're looking at. Parameters are never what they should be. A lot of stuff can go wrong, but it was really, I think, a rich learning process. In any case, then we applied it to a system for which we had absolutely no model at all, and then you could, of course, just sort of apply this procedure and get some number out of it. And then, from there, we could kind of guess at what kind of, model you could maybe build of the system. So basically there is some, so you could say that's a motivation for, trying to study this kind of thing from the data, that you don't start with any kind of models in your head, or, you of course expect that maybe, at least, so some things I suppose should hold, in the sense that you expect that maybe the system is describable by a Markovian, either finite space or continuous state space or something, but you don't start with any parameters, or you don't start with any model, but maybe, this kind of analysis could help you build, some kind of model for the system. So that's interesting. Okay, so and maybe I should actually also stop right away. So, things to follow up on. Well, there are, of course, many. Among them is, the sort of a very broad topic is, of course, the very applicability of the stochastic thermodynamics. As I mentioned, though I didn't specify the details, there are many, there are many assumptions that go in there. So some of them, for example, is that, for every process, so for every pair of, so remember this B and C in our state space, there are transitions between B and C, but, I can only describe systems where there are transitions back again. So that's one of the things, for example, which might be, so when you have this extremal statistics result, which I showed you right in the beginning of Satya and his student, there, maybe that's where you get stopped a little bit in applying this formalism there. So the thing is, can you generalize stochastic thermodynamics to things beyond what it's known? Or maybe you can't, but it's anyway something that people are interested in just now. Even, processes with memory, like Rosemary talked about this morning. Okay, and then, these, so now, so there are also these numerical schemes for understanding these entropy productions, so there are several of them now, including the short time TUR that I mentioned just now. I don't think that anyone's done a very systematic study of, comparing, for example, which scheme is better, because they all come with their own package of errors and assumptions and so on. So which scheme is better than what, or maybe it depends on the experiment, etc. And hybrid schemes would also be interesting, because there are some of these biological systems, like for the kinesing motor, where you describe it by something which is in discrete state space and something else which is continuous. So a hybrid scheme could also be very interesting to understand. And of course, the short time behavior, there could be a lot of subtleties in the short time behavior that we really need to understand. We know it works, but there is things to understand there also. And of course, now that we got into experiments or analyzing experimental data, we realize there's actually incredible amount of stuff one can understand about the kind of sort of data you get from experiments, so the errors which are somehow built in some way. In a lot of cases, it's not really known. One doesn't have any kind of, even in simple models, any analytical expressions for the kind of errors that or well, I wouldn't call it errors, the kind of constraints that experiments have in giving you the data. So those kind of things are also very interesting to think about, I think. Okay, and then with that, I think I'll stop. Thank you.
Okay.
And I still can't see any of you, so maybe I will have to stop sharing.
Okay. Yeah, thank you, Shupriya, for a wonderful talk. I think there was there are a few questions. Yeah, Prashant, there was one more before I just missed. I think PK you had. Yeah, PK, maybe you can ask first. Yeah.
Yes, now I can see you. Yes.
The question is that it is possible that in a system that there are in a large part in the configuration space the detail balance it works, but only one link breaks it. So the system most of the time lives in a part where the detail balance is working, and in a short in the time scale which you are looking at, there is no way to know whether it is equilibrium or not.
Mm-hmm. You mean because mostly it's in equilibrium, but maybe there's a small part of the phase space where it's not?
Yes.
So are you asking if people have looked at systems like that, or?
Yeah, I'm asking that is there a way to know even how exactly to know that whether it is equilibrium or not equilibrium? I mean, from a short time scale data, how exactly one knows that it is equilibrium or not? Because there can be systems like this.
Yeah. So of course then so when I say short time data, okay, so there are some subtleties there, right? So of course, what we would want, I mean, if we want to get this variance, nicely averaged, is a lot of data, but which you break up into these small sort of short time segments. But then if it's only some currents which point out the existence of the system not being in equilibrium, then of course we expect that the data should contain that information. Otherwise, you're never going to be able to see it. So we just have, so we would need that basically. So basically, that current, that one current, let's say, that is picking out that non-equilibrium behavior is something that you need in the data. Otherwise, you're never going to be able to see it. So.
Yeah, I have other questions, but I will be in the discussion too.
Yeah.
Okay. Thank you, PK, and thank you, Supriya. And Prashant, you have a question?
Yeah, actually, I had a question. First of all, thank you for the nice talk. So my question is, a non-equilibrium system can arise like probably in two ways. Either they are driven from the boundary, or in the context of active particles, we say like each of the particles are driven. So my question is, can any of the diagnostics that you presented be used to differentiate between these two non-equilibrium systems?
So different ways for a system to be, okay, yeah, so whether,
Yeah, like in one case, the system is driven out of equilibrium from the boundary, and in the other case, there's local drive at each of the constituent particles.
Yeah. So I think there is perhaps a way to think about them. So there is perhaps, but in the context of whether we are talking of maybe whether the system is being described by either sort of a Langevin or a master equation, I think. So in the Langevin sense, there is so if you're talking of overdamped Langevin equations, there are two ways that you can actually get this system to be out of equilibrium, or rather have a non-equilibrium steady state. And that is in one case you have like some time-dependent driving. In the other case, you have some non-conservative forces. Okay, so there are these two different ways. And between those two different ways, you can certainly find a way to, I think, sort of differentiate between those two. If you have active particles, on the other hand, I'm not, so I'm not quite sure, because, active particles can also be, and they often are also modeled by these sort of coupled over-damped Langevin equations, perhaps with some non-conservative forces. So I don't know if they fall into that category. But I think, in principle, there are ways to distinguish between them, I think, at least in some of those different schemes.
I see. Thank you.
Okay, thank you, Prashant. And maybe we can take other questions in the breakout room, Arnav, and we should thank the speakers here.
Okay, sure, no problem.
We would like to thank all the 4 speakers of the session, Rosemary, Prabhatosh, and Herbert, and Supriya. And over to Arnav.
Yeah, okay. Thanks a lot, Shraddha, for managing this session. So now we are closing the academic session, but the breakout rooms are open. So I'd request all the speakers to join. I mean, the rooms are named after them right now. If you could just wait a bit and join in the correct room. And all the other participants who have some question for them, just join that room. And we will start formally again in at 5:15 Indian time. So that's like 1 hour, 10 minutes. Okay, thank you again.
Where can I find the room? Sorry.